motion capture can produce realistic animations of human motion. However, by itself, motion capture can only reproduce motion. In this video, we will show how to use a set of motion capture clips to build a structure called a motion graph. Motion graphs can generate continuous, controllable, realistic motions. We build a motion graph by automatically detecting and creating transitions between clips. Here we show a simple motion graph built out of two clips. Any walk on the motion graph corresponds to a valid motion. This motion is generated through a random walk. The upper right contains a schematic of the motion graph, and the original segment of motion that is currently in play is shown on the left. Our technique scales to larger datasets. This is a random walk on a motion graph built out of the 12 clips shown at the beginning. We can search a given motion graph for a motion that travels along a user-specified path. Given just this one sneaking motion, a user can direct the character to sneak down different paths. Note that the integrity of the original motion is preserved. Larger motion graphs allow us to fit to more complicated paths. The duration of this motion is approximately equal to the amount of time necessary to extract it from the motion graph. Our algorithm works for motions that are not obviously locomotion. This new motion consists only of pieces of original motion capture data and blends used to create smooth transitions. No other warping was done to make the character follow the given path. Larger motion graphs may contain different kinds of actions. Here is a random walk on a motion graph built out of walking, sneaking, and martial arts motions. A user can direct a character along a path while simultaneously requiring specific kinds of motion to be performed in different sections. For each node in the motion graph, we can pre-compute fits to paths in a sampling of all possible directions. This allows us to interactively control the direction of the character.
In this paper, we describe a two-level statistical model called motion texture for synthesizing character motion that is statistically similar to captured human motion. A motion texture is a two-level statistical model. Motion texture is learned automatically from motion capture data. Each texton is represented by a linear dynamic system, or LDS. Several segments can be represented by a single texton. The distribution of textons is represented by a transition matrix. Given a learned texton and initial poses, we can synthesize a motion sequence frame by frame by simply drawing samples from the noise term. However, the dynamics may deviate from the original one as time progresses, as shown in the middle sequence. We fix this problem by setting the end constraints of the texton, as shown on the right. On the left, when two segments are synthesized from two textons and concatenated together, a jump is visible at the transition. On the right, the transition is smooth after we impose end constraints for the first texton. Here we show another example. Cyclic motion can also be synthesized easily. Motion at each cycle is differently sampled. From a single texton, we can synthesize characters with fine details while keeping the same dynamics. Fine motions can be edited at the texton level. For example, we can change the pose of an intermediate frame of a texton. By setting the new pose as an additional constraint, new motion can be synthesized easily. With the learned texton, we can not only synthesize the original motion as shown on the right, but also extrapolate new motion dynamics. Simply linear interpolating to a longer sequence would have slow motion effect, as shown in the left. Our algorithm extrapolates dynamics well, as shown on the right. Given two textons, our algorithm automatically finds the optimal in-between texton path.